Okay, so differential equations, what are they? What are they? A differential equation, so these are some vocabulary words that I'm going to walk you through. They almost say themselves. A differential equation is an equation that has derivatives in it. And then I'm going to show you what the textbook says. An equation that contains an unknown function and one or more of its derivatives. There are a lot of differential equations out there. If you look up what is a differential equation, you're going to see things you haven't even gotten into yet. As far as you're concerned, everything we've been doing is we've been solving integrals. We have been solving differential equations. Anytime you see y prime equals, it's a differential equation. And we've been solving the most basic differential equations. We're now moving up a step, and we're going to be able to solve a little bit more of some differential equations today. But realize that there is a giant world of differential equations out there that you haven't even seen all the symbols that they start using. Now, an important word you're going to hear is order, the order of a differential equation. Basically, it's a number, and that number is the, shall we say, farthest derivative. The highest number, I want to say highest order derivative, but then that's using the word. And they do that even here. So those of you who who love your English classes, I apologize for the definition using itself. The textbook does do that. The order of a differential equation is the order of the highest derivative that occurs. So it's the highest derivative number, basically. Okay. Highest derivative number in that differential equation. And I've got to tell you that as you take lower division courses, you won't go past a second order differential equation. In fact, second order are the challenging ones. You're only going to be dealing in this class with the most simple of the simple. Once you're done with second semester calculus, you'll have the option to take a lower division differential equations class. And it has been described as a cookbook class because it's full of recipes. If you see this, do this. And the understanding of why you use that technique, in that lower division class, you'll just use it and experience the fact that it gives you an answer that actually does work. But depending on the school you go to, usually it's not until upper division that you look more into why that process works, because that is far more difficult than just using the process. So know that there is just an entire branch of math devoted to differential equations inside of the calculus bubble. So you need to understand what they mean by a solution, and also that your textbook isn't very good about clarifying how far they want you to go. Once you don't have derivatives anymore, it's a solution. However, you're going to see that sometimes the textbook will take the problem all the way to isolating the dependent variable, or the y, in terms of the other variable. but that's not always going to be possible for these. So what you're going to find is the solutions that cannot have their dependent variable isolated, they're not going to isolate it. The ones where you can, they often do without really telling you, hey, I want you to isolate it. Know that on a test, I'll be clear if I want you to isolate your y, and the AP test is also. When you're expected to isolate your y, it'll usually say solve y equals f of x. It'll say something like this in there within the directions to let you know you're finding more than just the solution. You're solving it, finding a solution, and then isolating y. So just know that the textbook isn't clear about when you're expected to isolate. Don't spend a bunch of time trying to isolate y's because some of them you can't. Yeah. Okay, initial condition. Basically, you know how when you integrate, you get a plus c in a known constant. An initial condition is a known point on the solution equation that allows you to know what that specific plus c is. So the plus c that you get due to integration can be found if you have an initial condition. The initial condition is not necessarily when t is equal to 0 or x is equal to 0. It's just any particular point that you happen to know on the solution equation. If you don't have an initial condition, you're only going to be able to find a general solution. A general solution is really just a family of solutions. And we've seen that every time we have plus c, we have like a bunch of graphs. We can see a bunch of graphs that are just vertical displacements of each other. But when we get into some more challenging differential equations, we're not going to necessarily get a solution that's actually a function. We can get a variety of things. And let me go back to the picture here. Okay, I want you to shrink, but you're not listening to me. Okay. So if you look at these curves, there's a yellow one, a black one, a pink one, a green, and a purple. Those are all solutions to one particular to one differential equation, but it's a whole family of possibilities. If you know a particular point on the solution, you can figure out which of these it is. Can you imagine that there's some particular point, maybe, well, unfortunately, I can't draw on this right here, but maybe the point's over here. Maybe the point's here, and you know it's the yellow function that you follow. Or maybe you have a known point, initial point over here, and you know that it's going to follow this black function over here. It's just realize we're going to be looking at things where you get a drastically different function depending on your initial condition. Some of these are going to be hard, if not impossible, to solve. That's why we have what are called direction fields, which I'm going to actually save for the end because it's easier to work with. I'm giving you on day 1 and day 2 the things you're going to need to practice for a longer period of time. And then ending with the thing that you really don't need to practice. It makes perfect sense. Or, well, I can't say that, but you know, it's a lot easier to make sense of, and you don't need to practice it so much. So anyway, when we solve when we find a solution, give an initial condition, we find a particular solution. Am I spelling correctly? Particular? Help me out, good spellers. I don't have my, I just realized every time I type, I'm using a bit of a safety net. And I'm not sure if I'm losing my ability to spell due to that safety net. That's the trouble with the English language, too. It's all sorts of weird. Oh, dear. So know that a general solution is more like a family of solutions, where a particular solution is one specific curve. And I want to add in that it's a specific curve while you are in a continuous solution. If we run into a discontinuity based on a known, and we've been following based on a known point, we can't just guess where we wind up on the other side of that discontinuity. So a particular solution has to be a continuous solution. Now, I'm giving you problems in section 9.1 like this, where you are going to show that a solution, and this is a general solution, that this general solution is a solution of this differential equation. What you're going to do is you are going to take the solution, find its derivative, and then you are going to plug the derivative into the y prime of the differential equation. You're going to take what y is equal to, and you're going to plug that into the y of the differential equation. Then it's a matter of playing with the algebra and not making mistakes to come to a true conclusion, which we're going to see here. There's another problem that I'm giving you in your homework where it's asking you to solve for some unknown variable. So basically, you're going to start off the same way of you'll be given a solution. You're going to take its derivative and plug them in. In fact, I believe the one that I'm giving you, you're going to find its first derivative. You're going to find its second derivative. Don't worry, it's not as bad as this one. And plug in the y prime, and the y double prime. And then play with algebra until you find a solution to the variable that's left over in there. For this problem, I want to point out to you, y is your dependent variable, t is your independent variable, c is representing an unknown constant. Yes, before we get this problem started, we're going to have to find the derivative of this. That's our first step, is just do the derivative. But understand that c there is an unknown constant. Therefore, when you take the derivative, you're differentiating it as a constant. So, are you ready? Are you differentiating already? Okay, differentiate away. I'm going to differentiate quietly while you differentiate, and I'm more likely to not screw up if I just write and don't try to talk at the same time. So we're all working. And I'm checking. It looks like you guys are either still differentiating or done. Some of you are still working on it. So we use the quotient rule. And I really only differentiated other than the quotient rule where I've got the blue. And I know it gets confusing when E is involved. So I just want to emphasize that for this first piece, that was taking the derivative of the high, derivative of 1 by itself, 0, plus constant multiple times the derivative of e to the t, which is just e to the t. And pretty much same thing for d low, except it's got a negative. Now, let's take a look at what that is. Let's simplify this fraction before we start putting it into equations. Learned that lesson last period. So I'm trying to first see if I can factor over that negative sign or that subtraction sign. Do you see some common factors? C times e to the t shows up on both sides of the subtraction. In the numerator, that's going to leave me with this. Minus this, but also negative. I'm going to make this negative come together and turn positive, and then write this. I can't write. This is why I said I need to just write and not talk at the same time. Now, can you see a little bit more simplification? Yep. I'm going to add some room in here. Damn it. And I'm just going to circle. They go bye-bye. So essentially, we have 2 times c e to the t. So this is my y prime simplified. I'm going to drag over this so I can see it clearly. And this equation. Okay. Do I have the equation on that? Yeah. Not that. Yes, that. Okay. I'm dragging these over so that I can more easily work with it where I see the answer to the derivative. Okay. Again, this is y prime. And then I have y. I'm going to substitute into y prime the equation that I got. And then I'm going to substitute the y in right there. And all of you are just working with this. Do that, play with the algebra, see where it takes you. I'm going to quietly do this so that I don't screw up my algebra because I'm not doing well at talking and writing at the same time this morning. I'm going to pause for a moment. At this point, it's just play with algebra, and everybody's got slightly different ways that they're going to play with their algebra. And I want you to first try this on your own a bit, but I don't have a lot of time to give you to work on it on your own, but ideally you would have some time. In our normal time of class, I would give you like 5 minutes at least to just see if you can get this algebra worked out. So stay ahead of me, and then I'm going to work some algebra at the same time. I'm going to pause for a moment as I'm working on just this piece that I emphasized with the parentheses because I don't want to have the 1/2. I get the common denominator, and as I look at this, I can see two options in dealing with this, because this is going to turn into the common denominator thing. For the numerator, I can choose to square my binomials and then hope that I don't screw up with my subtraction or my squaring of binomials. But I also know I'm going to be less likely to make a mistake if I notice that what I have is a difference of squares. So what you can do is, if you want, check out what happens when you square these binomials and then properly subtract and see what gets rid of who. In the meantime, I want to show you that this is actually a little bit nicer to use when you're familiar with certain algebra properties. I don't know if I'd say properties, but certain things that occur in algebra, it can sometimes save you a lot of algebra time. What I see here is a difference of squares. Does that phrase all by itself sound familiar? No, you didn't change the color. I said change the color. Thank you. Okay. Oh, I had to push OK. Okay, so I'm going to emphasize difference of squares. You've heard that phrase before in factoring. How does a difference of squares factor? And I'm going to point that out with something that's you're familiar with. Yeah. You're familiar with something like maybe, can you factor x squared minus 25, a difference of squares? You know how that factors. I know you do. When you take this to a bigger algebra game, what you want to realize is when you have a difference of squares, it factors into a pair of conjugates where the square root of the squares are what you wind up, I wanted a different color, are what you wind up getting for the two sides of the plus and the minus. So when I go about factoring this difference of squares, for this subtraction, I'm going to put a plus and a minus. Then I've got a first term of that difference of squares. Its square root is 1 plus c e to the t. I'm going to put in unnecessary parentheses just to help emphasize that we're square rooting that piece. Then the square that is being subtracted gets the opposite signed things, and the square root of that is going to be just what's in the parentheses. I've got a lot of unnecessary parentheses in there, but I just wanted to overemphasize what was going on. Now when I take a look into it, I have 1 plus 1, and do you see that these are going to subtract themselves out? And then I want to be careful on the other side, because on the other side what I have is a c e to the t minus a negative c e to the t, and this time 1 minus 1 subtracts each other out. And so now this first factor simplifies to the number 2. This second factor, when I subtract the negative, I'm going to go ahead and go dink, dink, for now I have c e to the t plus c e to the t, giving me 2 c e to the t. And that's what I wind up getting for that second factor. And this is about as simplified as I'm going to get it. And now it's time to go back to where that came from. I hope can you guys see the screen okay? I'm trying to be able to have you see everything. So I'm right now writing what is here, 2c e to the t over parentheses 1 minus c e to the t squared, and then equal to 1/2. And then all that time was spent on what that 1/2 is multiplying by. And I need to bring up this simplified. Oh, I think I can lasso it. Ooh, ding, lassoed. Move, 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 move. Oh my goodness. Oh. Sometimes it is less writing when you are on a computer. That just made me happy because you usually have to sit there and rewrite that whole darn thing. You are probably. So I just shoved in there what I finally simplified everything down to. And then I can see I've got a 1/2 and a times 2. And take a look. I now have that left side, 2c e to the t over 1 minus c e to the t quantity squared is equal to 2c e to the t over 1 minus c e to the t squared. Oh, truth. So when you are trying to show that a function or an equation, I should say, wait, was could you scroll over to the left? Yes. When I need to show that an equation is a solution to a differential equation, my process is the equation you're trying to show is a solution. You need to find its first derivative. If your differential equation has a second derivative, you additionally need to take the derivative again. And then you're going to plug into the differential equation probably it would be preferred a simplified version of your first derivative, your function that you, or the equation you were given, and play with the algebra until you reach a point of it says true. Now, let me tell you what's absolutely wonderful about this. If you take a differential equations class in the future, I loved the fact that, and some of you will understand, after I did a problem on a test, when I solved a differential equation, I could check my work and see if I got the right answer by doing what I just showed you here. So you'll learn some process of getting from where is it? You'll learn processes of how to go from a differential equation to the solution of the differential equation. You'll actually be going that direction. You check your own work by taking that function that you just got, find its derivative, plug it in. Do I get a true statement? If you do, you know you did it right. Of course, you have to have enough time during the test to do that, but I loved that I could double check my work and then go on a search for where is my algebra mistake and hopefully find it in time. Some of you are like that and you get it. I always wondered, why do people just do it once and turn it in early and then they're done with it? But those are usually people, well, sometimes they're people who aren't as concerned about getting an A+, you know. All right, anyway. That was one thing you're going to be doing. Now on to the next thing, separable equations. You're going to be solving separable differential equations, and this is section 9.3. These are only going to be nice problems that just happen to work out. Be aware if you decide to try problems I didn't assign, you might run into advanced integration techniques from chapter 7 that I never taught you. So be aware of that if you are trying to do other problems in the textbook. I'm specifically assigning you problems that you have the integration skills to work with. So you're running into a situation where you can separate x and y into different factors. That will allow you to take the differential dx and multiply it over to the right. And then you can divide by the factor that has y in it. And that allows you to have a function, or an expression, I should say, with y times dy equals an expression with x times dx. And at that point, you're able to move forward and integrate. The only thing, or the main thing that's new, is the fact that you can separate, and the fact that you're going to be solving 2 integrals now instead of 1, and little tiny things. So here we go. First example. Insert some space. Insert space. There we go. Draw. It's very important that you make sure, as you do the algebra and move things around, dy must be multiplied to everything that is going to make up its integrand. Dx has to be multiplying by everything that makes up its integrand. Know that that is a key issue. I'm going to multiply y squared over to the left, and I'm going to multiply dx over to the right, and I'm now separated. I'm now going to integrate both sides. With respect to y, I'm integrating y squared. And it is an indefinite integral, so that means I have a plus c. I'm going to put plus c sub 1. On the other side of the equation, I am, with respect to x, integrating x squared. It is an indefinite integral. It also gets a plus c, and I'll put c sub 2. Now, if you step back and look at that, do you see that it was unnecessary to put in both? If I have an unknown constant adding to one side of the equation and another unknown constant multiplying or adding to the other side of the equation, I can just bring them together. So I could basically say subtract c1 to the other side, and now I have a subtraction of 2 unknown constants. And what's the subtraction of 2 unknown constants? An unknown constant. So what you will end up doing is you will put plus c on one of the two sides. Typically, people put it on the right side, but it technically doesn't matter which side you put it on. So what you're going to end up doing is, when you see this, you're going to go, okay, y cubed over 3 equals x cubed over 3, and then plus an unknown constant. Ooh, and do you want to see even more fun stuff? Because if I multiply both sides by 3, if c is an unknown constant, what is 3c? An unknown constant. Now, if you are doing this formally, it is important that you don't use the same the same symbol twice. I used a C sub 1 and a C sub 2 and a C. So what I'm going to do this time is I'm going to just put a C sub 3, although I think that might be too many threes. How about, because that's going to, I'll put a plus capital K. Basically, you can change any unknown constant expression into another looking unknown constant. You're allowed to do that. If that confuses you, don't do it, and it's a non-issue. Now, the problem asked me to first solve the differential equation. I was actually solved at this point right here. Solving a differential equation means getting to the point where you no longer have derivatives. Oh. So you omit the coefficient of the unknown constant. Oh, yeah. If you left the 3C as 3 times C, nothing would show up differently. It's perfectly fine either way. If what I just did in changing 3C to a different letter, if that confuses you, just don't do it. Now, this is officially solved. You will find that if you are able to isolate y, your textbook will isolate y. So that means that I'm getting the cube root of x cubed plus an unknown constant. So that's part A in just solving the differential equation. Again, this was enough to say I have solved. The next one is find the solution of this equation that satisfies this initial condition. In other words, they want you to find a particular solution. And we're able to find a particular function in this case. So we are going to plug in 2 for y, 0 for x. And if you had left the 3c as 3c, this would have been 3c. And when you find that unknown constant, as long as you plug it back into where you found it, you're going to end up in the same place as if you did change it. So when I solve for k, I have to put it back where I found it. If you were using this equation and plugged in the numbers, you would need to put it back in here. That's all. And when I look at that, I see that I cube both sides to get 8. And that is what k is. And the answer to part A is the cube root of x cubed plus 8. Done. Now, looking at the time, I know that there is something I need to show you. I'm going to do example 2 quickly. And then I have another example I need to show you so that you get why certain things happen in your homework. So I'm just going to quietly do this. I multiplied the denominators to the other sides. Done. It literally can be that fast. And I want you to notice, if you look at where y is, do you see there's no way you're going to isolate that thing? I swear it's not COVID. It was a throat tickle. So in this situation, this would be as solved as you would be expected to do. Now, I'm going to grab an example that I did over here, because I just, hold on a second. Trying to remember what I did. Okay. Yeah.
Second question. So for the equation with the plus c, could you put it on either side and it still be correct?
Yes. Yeah. And if you go through and plug in the known point, it'll come out the same equation no matter where you put the plus c or how you play around with it. The main thing is where you plugged in the numbers of the initial condition, that's who you have to go back to when you find your unknown constant.
So will you put it on the right side more to still be able to isolate y closely?
Yeah. Yeah, and that's often why it's done. And then what was I? No, trying to remember. How much time do we have left in class?
9 minutes.
Thank you. Okay. We are going to solve this differential equation given this initial condition. Here we go. Oh, also, this part of the directions emphasizes that you're going to isolate y. Your textbook never uses this in their explanations, but know that the AP test does. They clarify that they want you to isolate y if they want you to isolate y. Now, know if you see y prime, that means dy dx. If you saw w prime, that would mean dw d whatever the variable is. That's the independent variable. It should be clear in a problem, but sometimes this textbook isn't clear. All right, here we go. Separating the x's and the y's. After separating, it's time for some integration. And I've got my plus c unknown constant. I can choose to find that constant right now if I desire. So how about we do that? I'm going to plug this in. And so x is 0, y is -5. -5 squared is +25. So my c is 25/2. And now I'm going to rewrite y squared over 2 x to the 4th over 4 plus 25 halves. Now, had I been smart about this, I might have multiplied both sides by 4 first and stayed out of fraction land. But no matter how you play with your algebra and maybe get a different plus unknown constant, as long as you put it back in exactly where you plugged in the x and y, you're going to wind up with the same exact equation as someone else who put it in a different stage. Now, you're expected to isolate the y, and there's some things that I'm going to tell you about and warn you about. I'm going to multiply both sides by 2. And now when I take the square root of both sides, I'm supposed to get a plus or minus square root. Now, here's the thing. If you have a particular known data point, you can only follow along the solution curve from that data point as long as that is a nice continuous function. Do you see that when y is 0, there's an issue? You've got a divide by 0 situation. The actual solution to this differential equation creates 2 different possibilities. I don't know if you remember when I was first showing you integration, I showed you the idea of how it can sometimes turn into a piecewise function with 2 different unknowns based on a discontinuity separating 2 halves, shall we say. That's this situation right here. We have one initial condition. Based on that one initial condition, I am either going to be dealing with y being positive numbers, or I'm going to be dealing with y being negative numbers. Because at y equals 0, I've got a discontinuity problem. Which means you have to figure out which one of these is it. And some of you may already see it. And yeah, don't worry about if you crash and come back. I've had that sometimes with you guys. Anyway, that initial condition. Look at that initial condition, and do you see the answer? The known point has a negative y value. If one of them is negative, the only ones are negative that I have for the continuous function. Realize that if you run into a plus or minus situation when you're trying to isolate your y, that initial condition determines which one you use. And you're going to run into that a little bit in today's homework. So there you go. That's the particular solution. Then for your homework, let me find. So since we got a couple minutes, I'll just pre-warn you. And am I remembering correctly? Yes. Okay. So I gave you number 1 and number 3A from section 9.1. So let me just emphasize that number 1 is you're trying to show this is a solution of this differential equation. So that's like that first example that I went over with you. You need to take what you believe, what you are told is the solution, find its derivative, and then put both of them in the differential equation, the y and the y prime, and see if you come up with a true statement. 3a is asking you to not only do that, but find out what r has to be equal to for this differential equation, or to satisfy that differential equation. And you have to do y prime and y double prime. But that's not too bad with the exponential function. So know that you have your y, you'll plug it in here. You'll find y prime, plug it in here, find y double prime, plug it in here, and then have fun with algebra until you can figure out what r has to be in order for that equation to be true. And section 9.2 is what I'm going to come back to in a couple of days. Because I'm saving it for last so you have more time to practice these. I gave you some problems in this 1 through 10 category. It just says solve the differential equation. Understand that that means as soon as you have derivatives no longer, as soon as you put on that plus c, technically you have solved that differential equation. The textbook picks and chooses when it feels like isolating y, just to warn you. But know that by those directions, you don't have to isolate y, but I recommend that you observe when you can and cannot isolate your y, just for your own algebra sense. Then the next set of problems are find the solution of the differential equation that satisfies the given initial condition. So you're going to find your plus c. You may or may not isolate y. And unfortunately, again, the textbook doesn't tell you when. Some of these problems, though, you have to decide between a plus and a minus situation. So make sure that if you are able to isolate y, that you do, is really what it comes down to. But don't waste too much time trying to isolate your y, because it may not be isolatable. All right, then our time is up.